what momentum is. And momentum is a quantity. It's something you can measure. And ultimately, when we say momentum, it's always an equation in physics, right? So I'll write the equation down first because we want to start there. But if you haven't noticed yet, there's a lot of equations, right? It's not the equation that's important, and that's something you're going to have to start getting past. You have to understand that there's some meaning behind here. So this is the equation for momentum. We use a lowercase p for momentum. And I'm not going to make fun of the fact that it's a p. M was already taken, right? So we're going to use something else. Just go up a couple of letters and use p. So we use that to represent momentum. This is a new term for you. And let's clearly see that it is the product of mass and velocity. You'll notice I also used the bars that represent the fact that it's a vector. So momentum, like velocity, has direction. We've been having a little fun in the old energy and work world where there is no direction. Either energy increases or decreases, but I didn't have to worry whether it was going left, right, up, or down, correct? Well, now that goes away for this topic. This topic has direction, and the momentum takes its direction from the velocity. So if an object's moving to the left, its momentum is to the left. I want to define what I think momentum is. And you're not going to see this in the textbooks. Some of them will kind of describe this, but this is what I really want you to think of momentum as inertia due to motion. That's how I want you to define in your head what momentum is. Momentum is a measure of an object's inertia due to the object's motion. See, we talked about inertia earlier this year, and if you don't remember, inertia is an object's resistance to change. I know that back then, in the early part of the years, that resistance was something about how big the object is. Bigger objects would be harder to start moving than smaller objects. So we'd say that bigger objects had more inertia than smaller objects, right? What I want to impress upon you is there's more to inertia than just the size of the object. So a way to consider this is to consider how difficult it is to change the object. So if I can make a small object go really fast, it can have the same resistance to change as a big object going really slow. Now, let's get to my example again, because I think this is where I want to spend more of our time. So let's say carpet and tile and antique wine glass from Grandma's collection. Antique wine glass from Grandma's collection. Both started the same height above the ground and dropped. Somebody's going to pay the penalty, right? So the wine glass on the right makes it to here, and the wine glass on the left makes it to here. Can we agree that at the instant they touch the ground, they both have the same velocity? That all good? Okay. This represents my initial condition. All right, there's going to be a change to the momentum of each glass, right? Because the floor is going to stop each glass. So after a short amount of time, probably something on the order of milliseconds, one of these pieces. One of these not pieces. What's the momentum of the wine glasses after they settled on the floor? 0, sure. We know that the final velocity is 0, so the final momentum is 0. All good? And that's true for both. Final velocity is 0, So final momentum is 0. Change in momentum is final minus initial. Which wine glass had a larger change in momentum? Why neither?
Because they both have the same final and initial.
That's right. So I was trying to trick you, but you will not be tricked. They both had the same change in momentum. Good job. Because they both touched the ground at the same velocity, and because they're the same size wine glass, they both had the same initial momentum, and they're both brought to rest from the action of the floor. So they had the same final momentum. All good? Mm-hmm. So it's clearly not the change in momentum that causes the wine glasses to break. That's not the thing that's squishy. We call change in momentum impulse. Impulse is an object's change in momentum. And so I want to, of course, write this a couple different ways. And I'm going to write this one, but this one is predicated on an idea that might not be obvious as to why I'm telling you. But I could write it like this only if the mass doesn't change while the object's momentum is changing. Does that make sense? Like the mass of the wine glass didn't change even though it broke. All the pieces are still there. I'm bringing this up because there are situations in which the mass might change while the momentum is changing. A rocket has a significant change in mass while it's launching, and therefore its momentum is changing, but its mass is also changing. Does that make sense? So there are situations in which the mass might change, and that might result in part of the change in momentum. Now, I like to talk about impulse as a cause and effect kind of relationship. And this side is the effect of an impulse. The effect of an impulse is what the change is. So if I say the wine glass experienced an impulse, the effect of that impulse is that its momentum changed. You follow what I'm saying? Something caused it. Now, I think you all know what caused it. The floor caused it. And I think you also know that why the floor caused it, right? The floor applied a force to the wine glass. So there's the cause portion and the effect portion of impulse. So the effect portion is easy to see. We can observe the effect. The cause part, a little more difficult to see. But we'll define the cause as the force applied over a period of time. So we will define the cause of an impulse. The squishiness of the floor isn't as much about softness as about time. In which instance does it take longer for the wine glass to stop? The carpet or the tile? Carpet, right. The carpet takes more time to stop the wine glass. Now, if you look at this cause and effect, right, this side, for the wine glass, it's the same, right? It's the same whether it hits the hard floor or the soft floor. So on this side, if it takes more time to stop, then you can use less force. It's force that breaks the wine glass. So if it takes less time to stop, you're going to need more force to stop it. Let's talk about the car accident for a minute. In the car accident, if you're being stopped by the dashboard, the pillowy softness of the steel dashboard of a 1957 Chevy, not going to take very long to stop, is it? It's not like the dashboard gives very much. But in a modern car, we have the deployment of a nice pillow, right? As they explode a pillow in front of your face, and then you start to deflate that pillow. Got the seatbelt. Seatbelts can stretch up to 3 inches during a car accident. I want you to go to your car today. When you put your seatbelt on, pull on it. Does it feel like it's going to stretch very much? But under the weight of your body, yeah, they'll stretch to increase how long it takes to stop and to keep you in the car. If you're in the back seat, you don't get the luxury of having an airbag. You get the luxury of the pillowy softness of the chair in front of you. That padding on the back of the chair isn't for the occupant in the front, it's for the occupant in the back. It's your airbag. Since you don't get one, you get the back of their chair, right? All of this is to increase how long it takes to stop. And that's only a part of it. Remember, the car started the accident way before you got involved. The car started squishing for a long period of time. And when the car exhausted its amount of give, then you deployed the airbag, hit the seatbelt, hit the dash. All the things designed to make it take as long to stop as possible. It can take 100 times longer to stop in today's cars than in cars in the 50s. That's 1/100th the force. Because there's an inverse relationship here. So if the punch is coming towards you and you're going to stop the fist, you can lean in and make that thing stop quick, or you can lean back, make it take longer to stop. What's it going to do? It's going to make it hurt you less. Why? So you can take the next one too, and the one after that, and the one after that. It's an exchange. Force and time. Good so far? So I want to rewrite this a little bit. I put the word impulse in the middle. I put effect on one side, and I put cause on the other. The cause of an impulse is a force, and the result, or the effect, is to cause a change in momentum. This is not much different. Work is also being done during this time. I want you to imagine that, in this case, like you, with the airbag and all of that, you're moving through some distance as the force is being applied, correct? So work is also being done. In that case, it's taking away your energy. At the end of the day, you're going to be at rest. So work was also done, but work doesn't have to be done when an impulse is occurring. Let me give you an example of a situation in which work isn't done, but an impulse occurred. If I take a tennis ball and I throw it at a wall, is it clear it'll probably bounce off the wall? Did the wall move? So there was really no displacement. The ball might have squished a little bit, but a force was clearly applied that changed the momentum of the ball. So although there might not be an appreciable amount of work done here, there was certainly an impulse applied to the ball. Now, I'm not saying no work was done, because as the ball squished into the board, we would say that that's a bit of a displacement. But the fact that the ball recoils off of the wall suggests that it probably retained a lot of its kinetic energy. It didn't come to rest. In fact, I need you to do something just to make sure you're really paying attention. Let's say the tennis ball has a mass of 0.25 kilograms and is thrown at 3 meters per second and recoils off the wall at 2.5 meters per second. Can you tell me what the impulse experienced by the ball is? Did you remember that velocity is a vector? And did you decide to make one of these directions positive or one of these directions negative? Because when you do this, remember, it's a vector. So let's say I make to the right positive. Then you would have done 0.25 times negative 2.5, because that's the direction it recoiled off the wall, minus 0.25 times positive 3, because that's the direction it was going before it hit the wall. Initial and final. That was a mistake I was afraid you might make. Got it?
Yeah.
All right.